So, you know how everyone's talking about clean energy these days, right?
Yeah.
And how hydrogen is going to be like super important for that.
Oh, yeah, definitely. It's a hot topic.
Well, there's this crucial reaction involved in making clean hydrogen for those, fuel cells.
Right.
It's called the water-gas shift reaction. Basically, it takes carbon monoxide, not exactly the best stuff for the environment,
No, definitely not.
and turns it into hydrogen. Pretty neat, huh?
Yeah, it's a pretty amazing bit of chemistry.
The catch is you need the right catalyst to make this reaction happen efficiently, especially at lower temperatures. That's where things get tricky.
Yeah, finding the right catalyst is a major challenge in this field. Lots of research going on there.
And that's what we're diving into today. This paper we found, it's using something called large language models, the same tech behind those AI chatbots everyone's talking about, to design these catalysts way faster. Instead of spending months reading through tons of scientific papers.
Oh, I feel that pain. Reading through those papers can be a real slog sometimes.
Tell me about it. But this, let's call it the AceWGS framework. It aims to cut through all that noise and pinpoint the best catalysts in a fraction of the time. Sounds pretty game-changing, right?
Absolutely. The water-gas shift reaction, it's really a cornerstone of clean hydrogen production, especially for fuel cells. And you're right, the challenge is finding catalysts that work well, are cost-effective, and can operate at those lower temperatures. This research is exciting because it addresses a big limitation of how AI has traditionally been used for catalyst design.
What do you mean?
Well, in the past, AI models mostly crunched numbers, like reaction rates, material compositions, that kind of stuff.
Right, so very data-driven.
Exactly. But they often miss out on all the super valuable information that's hidden in the text of research papers, like the detailed methods scientists use to actually make these high-performing catalysts, the step-by-step recipes for synthesis. That stuff's usually buried in paragraphs of text, not neatly organized in a spreadsheet. So it's like trying to bake a cake with only a list of ingredients and no actual instructions. You wouldn't get very far.
Exactly. And it's not just about the missing information. Designing catalysts is this incredibly interdisciplinary field. You've got chemists, material scientists, engineers, and now more and more computer scientists all working together.
Right. Lots of different perspectives coming together.
Yeah, and each of those fields has its own jargon, its own way of communicating. Sometimes that can create barriers to real breakthroughs. It's like everyone's speaking a slightly different dialect.
And that's where AceWGS comes in, right? It's like a universal translator for catalyst design.
Exactly. AceWGS is designed to bridge those communication gaps. It lets researchers from all these different backgrounds talk to an AI system using natural language, the way we normally talk and write. That makes it so much easier to ask questions, find the information they need, and collaborate more effectively.
So how does this whole AceWGS thing actually work? What are the key parts? Well, they've built it with two main components. First, there's a user-friendly interface, a GUI, that makes the whole system really easy to use.
So no need to be a coding whiz to use it. That's good.
Exactly. And then, behind the scenes, you've got the brains of the operation. An LLM-based system that uses something called retrieval augmented generation, or RAG.
RAG, huh? Sounds a bit technical.
It is, but the idea is really cool. Think of it like this. You give the LLM access to a massive library of research papers.
Okay, so it's got all this knowledge at its fingertips.
Right. And as it's trying to answer your questions, it can pull out the most relevant information from those papers and use that knowledge to give you a much better, more accurate answer.
So it's not just spitting out generic responses. It's actually tailoring its answers based on the latest research.
Exactly. And there's this clever switch module they built in that acts like a traffic controller.
Okay, I'm intrigued. How does that work?
So based on what you asked, find me the best catalyst for low temperature WGS versus explain how CO oxidation works. This switch module directs your question to the right part of the system. It makes sure you get the most relevant answer possible.
That's pretty smart. And it's all built using open source tools, right? So other researchers can easily access and build upon this work.
Exactly. They use Python, a graphical interface built with Kinter, LangChain for managing the LLMs, and a Llama for running the AI models locally. It's great for accessibility and transparency in research.
Now let's talk about what AceWGS can actually do. The paper highlights 4 main features. The first one is being able to answer general questions. Why is that so important?
Well, think about it. Catalyst design involves so many different fields. You might have a chemical engineer who's suddenly having to learn about machine learning.
Right, a whole new world for them.
Exactly. They might have basic questions about, say, inverse modeling or generative AI. Instead of spending hours searching for intro materials, they can just ask AceWGS in plain language, and boom, it gives them a concise, relevant answer based on its knowledge.
So it's like having an instant expert on call.
Pretty much. It's all about breaking down those learning curves and making sure everyone's on the same page, regardless of their background. And the best part is it uses readily available open source LLMs for this.
That's fantastic. The second feature is all about extracting information from databases. It seems like a great way to utilize the huge amount of research that's already out there.
It is. The researchers put together this really impressive local database of 82 research articles, all about noble metal catalysts for the water-gas shift reaction. They focused on papers published between 2013 and 2021.
So pretty up-to-date research.
Absolutely. And this actually builds on a previous database that covered research from 2002 to 2012. It's like a super organized table with key information about each paper title, authors, year, and the abstract, which is super important.
So AceWGS can just search through this database for any relevant information.
Oh, it's much more sophisticated than that. They use this cool tool from LangChain called Create Pandas Data Frame Agent.
Pandas Data Frame Agent.
Yeah, it sounds complicated, but basically it lets the LLM understand the structure of the database.
Yeah.
It knows what each column represents, what information is in each row. So if you ask something like, find all the papers from 2021 that mention platinum nanoparticles on alumina, the LLM can actually generate Python code to search that database and get you precisely what you need.
So it's like having a research assistant who's fluent in both English and Python. That's pretty powerful.
It is. It takes data mining to a whole new level.
All right, on to the third feature. Comprehending entire research articles. This is where things get really interesting. Now, we're not just skimming summaries, we're diving deep into the details.
Exactly. For this, AceWGS uses that same LLM agreg framework, but this time it's focused on the full text of the articles. So you pick an article from the database and you can ask AceWGS specific questions about it.
I like it. So what were the key findings of this study? Or did they mention any alternative approaches?
Exactly. And it uses a very clever vector retriever tool to find the most relevant parts of the article to answer your question.
Okay, let's break that down a bit. How does this vector retriever thing actually work? How does it find a needle in a haystack of scientific jargon?
It's a multi-step process. First, they take the PDF of the research paper and extract the text. Then they split it into smaller chunks, about 1,000 characters each, with a little overlap to keep the context clear.
So like breaking a long story into digestible paragraphs.
Exactly. Then comes the really cool part. Each chunk is transformed into a vector embedding. Think of it like a digital fingerprint that captures the meaning of that text.
So it's not just looking at words, it's understanding the underlying concepts.
Precisely. They used a model called MexByEmbedLarge from Alma embeddings for this. And then all these embeddings are stored in a special database called a face vector database. It's designed for super fast searching based on meaning.
So when you ask a question, it's not just matching keywords. It's finding the parts of the paper that are semantically closest to your query.
That's it. It's like it actually understands what you're asking and can point you to the most relevant information, even if the exact words aren't there. Pretty amazing stuff.
All right, now for the big one, the feature that really blew my mind. AI inverse modeling. What's the deal with that?
So inverse modeling is all about reversing the traditional approach. Instead of starting with a catalyst and predicting how it will perform.
Right, the classic way of doing things.
You start by defining the performance you want, say a really high CO conversion at a low temperature, and then the system figures out the best catalyst and reaction conditions to achieve that.
So it's like saying, I want to get to Paris in under 5 hours. Tell me the best route and the fastest car.
Exactly. That's a great analogy. And AceWGS tackles this really complex problem using several tools. First, there's a graphical interface where you can specify all the parameters you want to consider, like the base metals, support materials, promoters, preparation methods, and the reaction conditions.
So you can really customize the search based on your specific needs.
Absolutely. Then, the heart of this feature is the inverse model itself. It combines a pre-trained AI model with a particle swarm optimization algorithm.
Hold on, a pre-trained AI model. Where did that come from?
That model was trained on all that data from the water-gas shift reaction databases we talked about earlier, but it also incorporates thermodynamic principles, the fundamental laws of physics that govern these reactions. So it's not just blindly searching, it's guided by scientific principles.
Smart. So it takes the catalytic composition, preparation methods, and reaction conditions as input, and what does it output?
It predicts the CO conversion you'd get with that combination, how certain that prediction is, and the theoretical maximum conversion based on thermodynamics. And then this particle swarm optimization algorithm, it acts like a super efficient search engine, using those predictions to explore different combinations of parameters until it finds the best one that meets your target performance.
So it's like a massive trial and error process, but done incredibly fast and guided by both data and scientific knowledge.
Exactly. And of course, it wouldn't be AceWGS without an LLM involved at the end, right?
Of course not. What does it do?
So the output from this inverse model is usually a bunch of numbers, right? Not exactly easy to understand at a glance. So they use a prompt-guided LLM to take those numbers and turn them into a clear, concise explanation in plain English.
So it's like the AI not only finds the answer, but it also explains it to you like a helpful colleague would.
Right. It makes those complex results much more actionable for researchers.
No, they also tested different LLMs to see which ones performed best within AceWGS. What did they find?
They evaluated 4 popular open source models: Llama 2, Llama 3, Llama 3.1, and Gemma 2, and they focused on those first 3 core features: general queries, database information extraction, and comprehending articles. They used the same settings for each LLM to make sure the comparison was fair.
So which one came out on top?
Interestingly, Gemma 2 consistently performed better than the others across those tasks based on the average user ratings.
Good to know. Gives us a sense of which LLM might be the best choice for this kind of work. Now, to really see this in action, the paper walks through a practical case study. They wanted to design a catalyst that works efficiently for the water-gas shift reaction at low temperatures, specifically below 300 degrees Celsius. How did they approach this using AceWGS?
First, they used the extract database information feature to quickly scan recent research for anything relevant to this challenge. They specifically looked for papers published in 2021 that mentioned MO, that's molybdenum carbide, in their abstracts.
So focusing on a specific material they thought might be promising.
Exactly. And this led them to 2 really important papers, one published in Nature and one in Science, both highlighting the potential of gold and platinum catalysts supported on something called alpha molybdenum carbide.
Saves a lot of time compared to manually combing through all those journals, right?
Yeah, absolutely. A huge time saver. Then they used the Comprehend Articles feature to really dig into those 2 papers. They could ask very specific questions about the catalysts used, the synthesis methods, even the step-by-step procedure for making the platinum catalyst on alpha molybdenum carbide using a technique called incipient wetness impregnation, or IWI.
So they could basically recreate those experiments just by asking AceWGS. That's amazing for knowledge transfer.
Exactly. Then they got creative. They used the Answer General Queries feature to brainstorm new catalyst designs based on what they learned from those 2 top-performing catalysts. And the LLM suggested some interesting ideas like alloying platinum and gold on alpha molybdenum carbide or carefully tuning the size of the metal nanoparticles to optimize performance.
So not just finding existing information, but also generating new ideas based on that information.
Precisely. Then they took one of those ideas, the platinum gold alloy, and used the AI inverse modeling feature to see if it could actually work. They inputted platinum, gold, and alpha molybdenum carbide, selected IWI as the preparation method, and set the target temperature below 300 degrees Celsius.
And what did the inverse model come up with?
It predicted that a catalyst with 4.26% platinum, 3.09% gold, and 92.64% alpha molybdenum carbide could achieve a maximum CO conversion of 95.07%, plus or minus a little bit, at a temperature of 200 degrees Celsius. It even provided specific recommendations for the initial gas ratios, the time on stream, and the ratio of catalyst weight to the gas flow rate.
So it basically gave them the recipe for this new catalyst and the optimal conditions to test it. That's pretty impressive.
It is. And because AceWGS had access to the full text of those papers, it could even tell them the exact steps for synthesizing the catalyst using IWI. It's a true end-to-end solution, from finding promising research to suggesting a new catalyst, and even providing the instructions to make it.
This case study really shows how AceWGS can accelerate the entire catalyst design process, from start to finish. It's like having a superpowered research assistant that can sift through mountains of literature, extract key insights, and generate new ideas.
I couldn't agree more. And the fact that it's open source and uses readily available LLMs means it has the potential to be a really transformative tool for researchers in this field. Plus, the authors have already outlined some exciting plans for future development, like expanding the features, automating data retrieval even more, and making it easier to create high-quality data sets to train even better AI models for Catalyst design.
Speaking of future directions, it's time for our Novel Notions segment. Based on what we've learned about AceWGS today, what are some intriguing, maybe even a little bit out there research directions this could inspire?
Okay, here's something to think about. Right now, AceWGS is great at analyzing existing catalyst formulations and suggesting variations. But what if we could take it a step further? What if it could propose entirely new support materials that haven't been used before for the water-gas shift reaction?
So not just tweaking existing catalysts, but coming up with fundamentally new materials.
Exactly. Right now, it analyzes textual descriptions of the properties of support materials. What if we could train the LM to understand the underlying reasons why those materials work so well, like their surface area, their thermal stability, how they interact with the catalytic metals, not just their names?
So it could move beyond just pattern recognition to a deeper understanding of material science principles.
Precisely. And then it could potentially suggest a completely new class of materials, maybe something like porous organic polymers, as catalyst supports, even if they've never been used for this reaction before. That would require the LLM to go beyond the existing database and make connections between material properties and catalytic performance that haven't been explicitly stated in any research paper.
So instead of saying, try a different metal oxide, it could say something like, based on what we know about how these reactions work and the properties you're looking for, have you considered a metal organic framework with these specific characteristics? That would open up a whole new world of possibilities.
Exactly. It would be like having an AI materials scientist on your team.
What's your second novel notion?
Okay. Building on AceWGS's ability to understand both data and text, could we develop a future version that could actually design the experimental protocols for testing new catalysts? Think about it. The methods sections of research papers are full of information about reactor designs, gas flow rates, temperature control, and how they analyze the reaction products.
Right, all the nitty-gritty details of actually running those experiments.
Exactly. What if an LLM could analyze all that information and learn the best practices for setting up these experiments? Then it could suggest an optimized protocol for testing a newly proposed catalyst, saving researchers tons of time and effort.
So not just designing the catalyst, but also designing the best way to test whether it actually works. That could dramatically speed up the whole discovery process.
Absolutely. Imagine an AI suggesting the ideal type of gas chromatography column and the perfect temperature program to analyze your reaction products based on the predicted reaction mechanism. That would be a game changer.
Both of these ideas are really thought-provoking. They show how LLMs could go beyond simply retrieving information and actually drive innovation in scientific research.
I agree. It's a really exciting time to be working in this field.
Well, this has been a mind-blowing deep dive into the world of AI-powered catalyst design. For our listeners who want to explore this further, the link to the AceWGS research paper is in the show notes below. It's a fascinating read.
Definitely worth checking out.
Thanks for joining us, everyone, and we'll catch you next time with more cutting-edge research.
Until next time.